How big is the universe, really? Have you ever stopped to think about it? Not just in numbers, but in actual scale. Imagine standing on Earth, looking up at the night sky. The stars you see, just the nearest whispers of a far greater cosmos. Now imagine zooming out. First, you leave the planet behind, then the moon, Mars. You pass the gas giants, Saturn with its shimmering rings, Neptune with its icy winds, and still you've barely moved an inch in the vast sea of space. This video isn't just about numbers or facts. It's about perspective, about stretching the human mind to its absolute limits. Because what lies beyond the edges of what we can see, beyond even the edge of our imagination, is more vast and more mysterious than anything we've ever known. The universe is not just big, it's staggeringly, unimaginably enormous. And today we're going to take a journey through it, step by step, layer by layer, zooming out from Earth until the very idea of distance begins to lose all meaning. As we move outward, we'll explore not only how far we can see, but how far we can think. From our solar system to the Milky Way, to galaxies and clusters and filaments that weave the structure of the universe itself. And then we'll push even further beyond what telescopes can see, into theoretical realms where the universe might not be alone, where parallel worlds might exist side by side with our own. This isn't science fiction. This is our universe, real, measured, observed, and yet still so full of mystery that even the greatest minds struggle to comprehend its size. So, take a breath, because once we begin to zoom out, there's no going back. What you're about to see will change the way you think about everything, not just space, but life, time, and our place in it all. How do we begin to understand the size of the universe? Perhaps the best way is to start small. To begin right here, on the ground beneath our feet. Earth, a planet spinning silently in space, a place that feels enormous to us. You could spend your entire life traveling its surface and still not see all the mountains, oceans, and cities that make up our world. But in cosmic terms, Earth is almost nothing, a speck of dust suspended in sunlight.
Let's take the first step. Imagine yourself leaving Earth's surface, rising slowly above the clouds. You see your city fade into the landscape. The roads become veins. The rivers shine like threads of silver. Soon you're in the thermosphere. The blue fades to black. The curvature of the Earth becomes visible, and with it comes a profound realization. Earth is round, fragile, floating.
You keep rising. Now you're far above the International Space Station, which orbits at just over 400 kilometers above Earth. Even here, in what we call low Earth orbit, you're still so close to the planet that it dominates your view. The entire station could fit inside one small corner of a city on the surface.
As you ascend, you pass satellites, thousands of them, spinning silently, transmitting signals and data, circling the globe in carefully calculated paths. Beyond that, there's only open space. The distance to the moon is your next stop. And here's where the scale begins to warp our minds. The moon is on average about 84,000 kilometers from Earth. That number sounds big, but what does it mean in terms we can grasp? If Earth were the size of a basketball, the moon would be a tennis ball sitting about 7 meters away. Not far in our everyday world. But in space, that's a vast emptiness, and in that void between Earth and the moon, there is nothing. No planets, no stations, no people, just silence. It took the Apollo astronauts over 3 days to make the journey to the moon, and that's just the first step away from our home planet. Because as soon as you reach the moon and look back, Earth already looks small, just a glowing blue marble floating in black. And beyond the moon, the scale starts to grow at an exponential rate. Let's move further. Mars, our red neighbor, sits an average of 212 million kilometers from Earth. That distance varies as both planets orbit the Sun. At its closest, it's only 54 million kilometers away. A journey that takes spacecraft many months to complete. Even with our best technology, we haven't sent humans there yet. We've sent rovers, tiny mechanical explorers, like Curiosity, Perseverance, and Spirit. They crawl across a dry, ancient landscape, shaped by winds, dust storms, and time. And when we watch their footage from Earth, we're looking at a world that in the grand scale of the universe is still just next door.
Now let's pass Mars and head for the outer planets. This is where the real emptiness begins. Between Mars and Jupiter lies the asteroid belt, a scattered collection of rocky debris that never formed into a planet. It's not the dense, crowded minefield often depicted in science fiction. In fact, the objects are so spread out that a spacecraft can fly through the belt without hitting anything at all. The void is immense.
Then we reach Jupiter, the giant, 11 times wider than Earth, more massive than all the other planets combined. Its atmosphere is a roaring, stormy swirl of clouds and colors, and its great red spot, a storm twice the size of Earth, has been raging for centuries. Jupiter's presence dominates the outer solar system. It's orbited by dozens of moons, including Ganymede, the largest moon in the entire solar system, even bigger than Mercury. Saturn comes next, a little farther out, famous for its stunning rings. From a distance, the rings look solid, like a vinyl record circling the planet. But zoom in, and you find they're made of countless chunks of ice and rock, ranging in size from grains of sand. The beauty of Saturn is deceptive. Its rings are paper-thin compared to the planet's size, stretching out for hundreds of thousands of kilometers, yet only a few kilometers thick. And still, we're not even halfway to the edge of the solar system. Beyond Saturn lies Uranus, a pale blue ice giant that spins on its side. Its tilted axis creates extreme seasons, with each pole getting 42 years of sunlight followed by 42 years of darkness. Further still is Neptune, a deep blue world with supersonic winds and storms that rage across its upper atmosphere. At this point, sunlight has grown faint, weak. It takes over 4 hours for light to reach this part of space. If Earth is your fireplace, then Neptune is standing outside the house with the door closed.
But we're still inside what we call the planetary system. Beyond Neptune is the Kuiper Belt, a region filled with icy remnants from the formation of the solar system. Here lies Pluto, once the 9th planet, now a dwarf, orbiting in a tilted, eccentric path.
When the New Horizons spacecraft flew past Pluto in 2015, it revealed a surprisingly active world. Mountains made of ice, nitrogen plains, and a heart-shaped glacier, the size of Texas. Pluto orbits at roughly 5.9 billion kilometers from the Sun. At this distance, the Sun looks like just another bright star. But the Kuiper Belt isn't the end. Beyond that lies the scattered disk, home to strange, distant objects with elongated orbits. And further still is the theoretical Oort cloud, a shell of icy bodies that may surround our solar system like a vast bubble. We've never seen the cloud directly, it's too distant, but it may be the source of long-period comets, icy travelers that occasionally dive toward the inner solar system, leaving brilliant tails in the night sky. So, where does the solar system end? There's no clear boundary, but scientists often define the edge using something called the heliopause. This is the point where the solar wind, the stream of charged particles flowing from the Sun, finally slows down and gives way to the interstellar medium, the plasma and dust between stars. The heliopause sits around 18 billion kilometers from the Sun, and only one human-made object has ever crossed it. That object is Voyager 1, Launched in 1977, Voyager 1 was designed to study the outer planets. But after completing its primary mission, it kept going. It's now over 24 billion kilometers from Earth, traveling at more than 60,000 kilometers. It carries with it a golden record, a message to any intelligent life that might one day find it, containing sounds and images from Earth, music, greetings, a map of our location. As of now, it's the most distant object ever created by humans. And still, it has not yet left the solar system entirely. Not if you define the solar system as including the Oort cloud. It could take another 30,000 years to fully escape that boundary. All this, from Earth to the heliopause, is just our cosmic backyard, and yet even this neighborhood is incomprehensibly vast. Let's put it into a scale we can grasp. If you shrunk the entire solar system to the size of a coin, just the orbit of Neptune around the Sun, then the nearest star, Proxima Centauri, would be another coin placed over 300 kilometers away. And that's just the next closest star. The Milky Way, our galaxy, contains over 100 billion stars. And yet, we're still zooming out from the surface of Earth to the edge of the heliopause. We've crossed distances we can barely imagine. We've seen planets, moons, rings, and comets. We've followed spacecraft and solar winds. We've watched the light of our sun fade into the void, and with each step away from Earth, one truth becomes clearer. The scale of the universe is not just large, it's fundamentally beyond our everyday comprehension. But this is only the beginning. Because once we leave the solar system behind, we begin to encounter even larger structures, neighboring stars, entire constellations, stellar nurseries, and eventually the spiral arms of the Milky Way itself. The distances grow so vast that we can no longer measure them in kilometers or miles. We switch to light years, the distance light travels in a year, nearly 10 trillion kilometers, and even then we're still dealing with numbers so large, they feel more like poetry than math. From here, we are about to zoom out even further, to explore our galaxy, the vast structures beyond it, and the shape of the entire observable universe. But for now, take a moment. Consider that everything we've discussed, the Earth, the Moon, the Sun, every planet, every comet, every spacecraft ever launched, fits inside a single star system. A system that in the grand structure of the cosmos is smaller than a grain of sand in a desert that stretches without end. And we've only just stepped off the porch.
We've now left our solar system behind, traveling billions of kilometers from the warmth of our sun. Voyager 1, humanity's furthest traveler, drifts silently in the cold dark, its golden record carrying whispers of Earth into the unknown.
Out here in interstellar space, the distances become so vast that kilometers lose meaning. So we switch to a new unit, the light year. 1 light year is nearly 10 trillion kilometers, the distance light travels in a year.
And now we begin to see the stars. They appear to us as distant specks, but each one is a blazing sphere of plasma, like our sun. Some smaller, some vastly larger. Some are burning hot and blue, others old and fading red.
The space between them is not empty. It's filled with a thin soup of gas, dust, and magnetic fields, a region known as the interstellar medium.
This is where we find ourselves now, inside a vast region known as the local bubble. The local bubble isn't something you can see. It's not outlined in glowing walls or obvious boundaries, but it's very real. It's a cavity, a sort of cosmic void within the galactic plane, stretching about 1,000 light years across. Our sun sits roughly in the middle of it, traveling slowly along its path around the Milky Way. So what is the local bubble, and why does it exist? Millions of years ago, massive stars lived in this region. Some of them were giants, short-lived and unstable. When they died, they exploded as supernovae, titanic blasts that release unimaginable energy. These explosions sent shockwaves through the interstellar medium, clearing out vast pockets of space, sweeping away gas and dust, and leaving behind a bubble-shaped void. That's where we live now, inside the remnants of a cosmic battlefield. The local bubble is a kind of scar on the galaxy, carved by ancient stellar deaths. It's not empty, exactly. It contains hot, diffuse gas, remnants of those explosions, but it's far less dense than the space outside it. As our sun moves through this bubble, it encounters varying patches of gas, including a particularly dense cloud known as the local interstellar cloud, sometimes called the local fluff.
Our entire solar system is currently drifting through this region, and the heliosphere, the bubble created by the solar wind, is shaped by the pressure of this surrounding interstellar material.
Now, as we float inside the local bubble, it's time to look around. Who are our neighbors?
The nearest star to our sun is Proxima Centauri, part of a triple star system called Alpha Centauri. It lies just 4.24 light-years away, a blink in cosmic terms, yet still far beyond the reach of current space travel. If you could ride aboard Voyager 1, it would take you over 70,000 years to reach it. Proxima is a red dwarf, smaller and cooler than the Sun, and it hosts at least one planet within its habitable zone, a tantalizing possibility for life. But we are still a long way from knowing if anything stirs on that distant world. The Alpha Centauri system is our closest companion in a wider network of nearby stars. Within about 10 light-years, there are over a dozen stellar systems, including Barnard's star, Wolf 359, and Luton. Many of them are red dwarfs, which are by far the most common type of star in the galaxy. They burn slowly and steadily, and though they are small and dim, they could shine for trillions of years, far longer than our sun. The stars within 25 light-years form what we call the solar neighborhood, a sphere of space that contains dozens of stars and brown dwarfs. Brown dwarfs are failed stars, objects too massive to be planets, but not quite massive enough to ignite fusion in their cores. They lurk in the dark, giving off faint infrared radiation, making them hard to find. Only in recent decades have we begun to detect these shadowy members of our cosmic community. Some of our neighboring stars are young, others are ancient. Some are solitary, others belong to binary or trinary systems, locked in complex gravitational dances that last for eons. Many have planets, and some of those planets may be rocky, Earth-like and temperate. The discoveries of exoplanets, planets orbiting other stars, have revolutionized our understanding of the universe. Thousands have been confirmed, and many of them are surprisingly diverse. Hot Jupiters, super-Earths, ocean worlds, frozen gas giants, and lava-covered infernos. We now believe that nearly every star has at least one planet. The idea that our solar system is unique has long since faded. Instead, we find ourselves in a galaxy filled with other solar systems, some wildly different, others eerily familiar, and all of them orbiting their stars in the quiet clockwork of the cosmos. But the space between these stars is immense. Even in the densest parts of our local neighborhood, stars are separated by light years of near emptiness. If the sun were the size of a basketball, Proxima Centauri would be another basketball placed over 7,000 kilometers away. That gives you an idea of just how vast these gaps are. and how isolated each system is. Now, zooming out a little more, we begin to see the shape of the local bubble itself. We're not alone in here. Other stars occupy this space, moving through it at different speeds and directions. As our solar system drifts through the bubble, so do they, in a slow, majestic dance choreographed by gravity.
The local bubble is surrounded by other bubbles, other cavities formed by ancient supernovae. Some have names like the Lupus bubble, the Scorpius Centaurus bubble, and the Orion Eridanus superbubble.
These structures overlap and interact, creating complex patterns in the interstellar medium. Our local bubble may one day intersect with another, or collapse entirely as the pressure from outside space reclaims the void. We know this structure through careful observation. Astronomers map the interstellar medium by studying the absorption and emission of light from distant stars. Certain wavelengths, like X-rays and ultraviolet, reveal the presence of hot gas and magnetic fields. These methods allow us to piece together a three-dimensional picture of our galactic neighborhood, one bubble at a time. There's beauty in this invisible architecture. The local bubble isn't something we can see with the naked eye, but we know it's there, shaping our environment, influencing the movement of cosmic rays, and forming the backdrop of our stellar voyage. Zooming out again, we reach a region called the local arm, or Orion arm, a minor spiral arm of the Milky Way in which our sun resides. We are situated between two larger arms, the Sagittarius arm and the Perseus arm. The local arm stretches for thousands of light years and contains hundreds of thousands of stars, gas clouds and nebulae. It's one of the galaxy's spiral tendrils coiled like a whirlpool around the galactic center. Our neighborhood is just a tiny section of this arm, but even here there are marvels. Massive star-forming regions, like the Orion Nebula, light up the void. Here, new stars are born from collapsing clouds of gas and dust. Young stars gather in clusters, surrounded by protoplanetary disks, swirling rings of material that may one day become solar systems like our own. These are the cradles of stars, the nurseries of the galaxy. One of the most fascinating aspects of the local bubble and its surrounding stars is that we're in motion. The entire solar system is moving through the galaxy at roughly 8 but because everything around us is moving too, stars, gas clouds, even other bubbles, it feels like we're standing still. Yet over millions of years, our position in the galaxy changes. We pass through different regions of space, and those regions may affect us more than we think. Some scientists believe that as the solar system travels through denser parts of the galaxy, we might experience higher rates of cosmic rays. These high-energy particles could potentially influence Earth's climate or even trigger mass extinctions. It's a humbling thought. The path of our solar system through space may have shaped the course of life on Earth. And so we begin to see that we are not just floating in space. We are part of a dynamic, ever-changing environment. The local bubble is not a static place. It's a moving, breathing region of space that has history and structure, and it connects us to the broader architecture of the galaxy. From Earth to the edge of the solar system, from the helipause to the neighboring stars, from red dwarfs to blue giants, from quiet planetary systems to violent supernova remnants, the scale has already grown 1,000-fold since we began our journey. But we are still only zooming out through one small part of the galaxy. We now understand that our place in the universe is like a grain of sand in a vast forest clearing. Around us, other grains shimmer, stars and systems, distant and unreachable. And as we look out, we begin to grasp the enormity of what lies beyond.
But our journey doesn't end here. Ahead lies the full spiral of the Milky Way, a galaxy with over 100 billion stars, clusters of stars, rivers of dust, arms of creation, and a supermassive black hole at its heart. And even beyond that, other galaxies stretching to the edge of the observable universe. But before we get there, take one last look back. From the outside, the local bubble would be invisible. But from within, it's everything we know. It's our cosmic neighborhood, it's home. And soon, we'll step beyond even that. We've left the warmth of our sun. We've passed the distant edges of our solar system, drifted through the local bubble, and watched the light of nearby stars fade behind us. Now we begin to see something larger, something that defies imagination. We see it not with our eyes, but with the composite knowledge gathered over generations, radio waves, infrared signatures, ultraviolet light, and the whispers of X-rays, pieced together like a mosaic over centuries. What emerges is the shape of home, not our planetary home, but our galactic one, the Milky Way. From within, we experience the Milky Way as a bright, hazy band stretching across the night sky. Ancient cultures saw it as a river of milk, a path of spirits, a celestial road. Today, we know it's something far grander, a barred spiral galaxy, more than 100,000 light-years across, made up of stars, gas, dust, and dark matter. Billions upon billions of stars like our sun, each with their own worlds. And we're just one solar system orbiting quietly in a minor arm called the Orion Spur, about 27,000 light-years from the galactic center. The scale of the Milky Way is difficult to comprehend. Even light, the fastest thing in the universe, takes 100,000 years to cross it. That means if a beam of light started at one end of the galaxy the day humans invented fire, it still wouldn't have reached the other side today. Our own solar system takes roughly 20-30 million years to complete a single orbit around the galaxy. We've only completed that orbit a few times since the Earth formed. The last time we were in this position, the dinosaurs walked the planet. If we could look at the Milky Way from the outside, we'd see graceful spiral arms curling out from a bright center like a cosmic whirlpool. Those arms, Perseus, Scutum Centaurus, Sagittarius, are lined with stars, nebulae, and dark bands of interstellar dust. They are not fixed structures, but patterns formed by density waves, regions where stars and gas bunch together like cars, slowing down in traffic, creating spiral lanes of cosmic congestion. Our galaxy spins. The central bulge, a thick golden heart, is composed of older stars, tightly packed and moving in complex orbits. Surrounding it is the galactic disk, thin and wide, where most of the star formation occurs. This is where our sun lives, drifting among the spiral arms. Beyond that is the halo, a spherical region sparsely populated with ancient stars and mysterious globular clusters. And beyond even that lies the dark matter halo, an invisible structure we can't see but whose gravitational pull binds the galaxy together. The Milky Way is not static, it evolves. Stars are born, live out their lives and die. Massive clouds of hydrogen collapse under gravity, igniting into newborn stars. Some will live for billions of years, others will burn brightly and die young. When the most massive stars reach the end, they explode as supernovae, ripping themselves apart and seeding the galaxy with heavy elements. Every atom of iron in your blood, every trace of calcium in your bones, every molecule of oxygen you breathe, they were all forged in stars and scattered into space. We are made of the galaxy's recycled matter. There are places within the Milky Way that defy belief.
the Eagle Nebula, where the pillars of creation stand like columns of smoke, stellar nurseries birthing new suns, the Lagoon Nebula, a vast cauldron of glowing gas, the Tarantula Nebula, a furious tangle of star-forming filaments. These are regions of raw creation, chaotic, dangerous, and beautiful. They exist because the Milky Way is not just a structure, it's a living system always changing. But for all the brilliance of these regions, the most mysterious place in our galaxy lies at its center.
At the heart of the Milky Way is Sagittarius A, a supermassive black hole containing over 4 million times the mass of the Sun. We can't see it directly, but we know it's there. We watch stars near the core whip around it at incredible speeds, pulled by an invisible force. This black hole is quiet for now, but there's evidence it was once active, spewing jets of radiation, perhaps influencing star formation across the galaxy. Even today, its presence is felt. Huge gamma-ray bubbles, called the Fermi bubbles, extend above and below the galactic plane, evidence of past eruptions. The galactic center is crowded, violent, and energetic. If we lived closer to it, life as we know it might not have survived.
And yet, despite the chaos at its core, the Milky Way is our shelter. It has protected us, fed us, and nurtured life. It has given birth to civilizations and ideas, but we are not its only inhabitants. The Milky Way holds more than just stars. Orbiting the galaxy are hundreds of satellite galaxies, dwarf systems like the large and small Magellanic Clouds, visible from the southern hemisphere. These are gravitationally bound companions, slowly being torn apart by tidal forces. Some will eventually merge with the Milky Way, adding their stars to our own.
And there's something even more startling. Our galaxy is currently devouring others. Streams of stars, long ghostly rivers, arc through the halo, remnants of past mergers. The Milky Way has grown by cannibalizing smaller galaxies, and it will continue to do so. In fact, in about 4 billion years, it will collide with the Andromeda Galaxy, our nearest spiral neighbor. This galactic collision won't be like a crash on Earth. Stars are so far apart that most won't touch, but gravity will reshape both galaxies, flinging stars into new orbits, igniting new waves of star formation, and eventually merging into a new, larger galaxy. Sometimes called Milkomeda, it will mark a new chapter in the life of our galaxy. Long after Earth is gone, the descendants of the Milky Way will continue.
For now, though, we reside in one moment of its long story. As we zoom out, we see the galactic plane tilt and rotate, a pinwheel of light against the backdrop of intergalactic darkness. We are part of that pinwheel. Everything we know, everything we love, every war and poem, every tragedy and triumph, it all happened on a tiny world orbiting one of 100 billion stars. The scale of the Milky Way humbles us. The distances between stars are vast, but even the width of the galaxy is nothing compared to what lies beyond. Our galaxy is just one of countless others, and yet this one is ours. It's the cradle of humanity, the nursery of Earth, the home of every living being we've ever known. It's been our silent guardian since before the first life took shape in the oceans. It moves through space, slowly spinning, arms outstretched as if holding us.
But it's not alone. As we zoom farther out, we'll see that the Milky Way is just a single thread in a vast cosmic web. There are other galaxies, clusters, superclusters, voids, and walls. The structure of the universe extends far beyond even this magnificent spiral. Still, before we continue outward, take a moment to appreciate the serenity of this view. A galaxy of stars, spinning in silence, shining across the abyss. A place of wonder and violence,
a structure made of fire and darkness, our Milky Way. This is the grand canvas on which the story of our existence has been painted.
As we drift away farther and farther, the spiral becomes a dot. The dot becomes a blur, and then it vanishes. We are about to enter the realm of the truly enormous, where galaxies themselves are the building blocks, and the universe reveals its most breathtaking scales.
But no matter how far we travel, one truth remains. We come from the Milky Way. It is, and always will be, our galactic home.
We have left behind our galactic home, the Milky Way. Its grand spiral arms slowly fade into the distance. The stars that once seemed so numerous now dissolve into a faint shimmer. As we zoom farther out, something extraordinary begins to take shape. The night grows darker, empty, quiet, but it is not truly empty. In the deep cosmic silence, a new kind of structure begins to emerge. Not stars, not planets, not even galaxies alone, but immense gatherings of galaxies, structures so vast they make the Milky Way seem like a mere grain of sand in a sprawling metropolis.
These are galactic clusters, the universe's cities of galaxies. Galactic clusters are the largest gravitationally bound objects in the universe. They are regions of space where hundreds, sometimes thousands of galaxies gather, held together by the invisible threads of gravity. They are colossal, often stretching millions of light years across. From a distance, they resemble brilliant clouds, glowing with the light of countless galaxies. One of the most well-known of these clusters is the Virgo cluster, our own cosmic neighborhood.
The Milky Way is not isolated. It belongs to a small group of galaxies called the Local Group, which includes Andromeda, Triangulum, and around 50 dwarf galaxies. The Local Group itself is part of the larger Virgo supercluster, whose heart is the Virgo cluster. As we zoom into the Virgo cluster, we see galaxies spinning silently, orbiting one another in vast orbits dictated by mutual gravitational pulls. Spiral galaxies with their winding arms, elliptical galaxies with their smooth golden glows, and irregular galaxies that seem torn and scattered, all coexist here.
Unlike individual galaxies, which are defined by stars and gas, clusters are shaped by an even larger, more elusive presence, dark matter. Scientists estimate that up to 85% of the mass in galactic clusters is composed of dark matter. We cannot see it directly, but we see its influence. It binds these galaxies together and sculpts the gravitational scaffolding upon which the visible matter clings. But that's not all. Clusters of galaxies are not just filled with stars and galaxies, they are suffused with hot gas, so hot that it emits X-rays. This intergalactic medium can reach temperatures of tens of millions of degrees. It is invisible to the naked eye, but when we observe these clusters with space-based X-ray telescopes, they light up like burning embers.
This superheated gas is a silent witness to ancient collisions, mergers, and the ongoing violence of cosmic gravity. One of the most dramatic examples of this violence is seen in the Bullet Cluster. It is not just a collection of galaxies, it is two galaxy clusters that collided. As they passed through each other, the galaxies themselves, being mostly empty space, slipped past relatively unscathed. But the hot gas between them collided, slowed down and clumped. Observations of the Bullet Cluster provided some of the best evidence we have for dark matter. While the visible matter slowed and clustered, gravitational lensing, a warping of background light due to gravity, showed that most of the mass had passed through undisturbed. The invisible dark matter kept going. In these cosmic cities, galaxies interact. They dance around each other, pulled by invisible forces, sometimes drawn so close that they merge,
When galaxies collide, it's not like two solid objects crashing. Instead, it's more like two clouds passing through one another. Stars might be flung into new orbits. Gas clouds may compress, igniting furious bursts of star formation. These interactions fuel the evolution of galaxies. In clusters, galaxies age faster, stripped of gas and transformed by gravity. Some become red and dead elliptical galaxies, no longer forming stars, their youthful fire extinguished by time and collisions.
And at the centers of many galaxy clusters lies something even more powerful. A giant elliptical galaxy, often the most massive type of galaxy in the known universe. These central giants dominate their neighborhoods. One such example is M87, the behemoth at the heart of the Virgo cluster. In 2019, M87's supermassive black hole became the first black hole ever directly imaged, a dark void surrounded by glowing plasma. That single image reminded us of the immense forces at play in the hearts of these cosmic cities.
Galactic clusters aren't randomly scattered. They tend to form at the intersections of the cosmic web, a vast structure of filaments and voids shaped by gravity over billions of years. Matter in the early universe clumped together, and over time, gravity pulled that matter into threads, knots, and nodes, creating a web-like structure. Galactic clusters sit like luminous cities at the crossroads of the universe, dense nodes where the filaments of the cosmic web converge. But they are more than just bright congregations of galaxies. They are central stations of the universe's vast transportation network, receiving and redistributing matter and energy like hubs on a cosmic highway. And yet, amid this bustling traffic of stars and gravity lies a paradox. Though galactic clusters are among the densest regions of the cosmos, they are also overwhelmingly empty. The space between galaxies in a cluster is not filled with light or life, but with endless silent, frigid void. Even within the same cluster, galaxies are separated by distances so vast that light itself can take millions of years to travel from one to another. Still, these galaxies are gravitationally bound, moving together like a school of fish in a cosmic ballet. Some lead, some follow, some drift behind, but all remain linked by an invisible thread, a shared gravitational choreography. And perhaps the most humbling fact is this: what we see is not the present, but the ancient past. Light from these clusters began its journey across space billions of years ago, before Earth had trees, before dinosaurs roamed, even before continents formed. Galactic clusters are not just structures in space. They are time machines, frozen records of cosmic history. They show us galaxies as they were, not as they are. Each cluster we observe is a chapter torn from the early pages of the universe's grand story, letting us witness how cosmic structures formed, evolved, and hinted at their fate. As we continue zooming out, these clusters reveal their deeper role as markers, waypoints in our quest to understand the scale of the universe. We begin to see a pattern emerge: the Virgo cluster, the Coma cluster, the Hercules cluster, each one a radiant ember in the vast dark sea of space. Yet they do not exist in isolation. Clusters group into even greater assemblies called superclusters. These, in turn, connect into colossal structures that span unimaginable distances. One such structure is the Laniakea supercluster, our cosmic home. Named from the Hawaiian word meaning immense heaven, it spans over 500 million light-years and houses more than 100,000 galaxies, including our Milky Way. It is but a single glowing thread in a web that stretches far beyond comprehension. At this scale, we begin to grasp our true place. not as inhabitants of a world, or a solar system, or even a galaxy, but as members of a larger gravitational community shaped by ancient collisions and governed by forces we cannot see. As we float farther out, galaxies disappear from view, clusters become faint dots, and eventually all detail is lost to a pattern, a woven tapestry of matter and emptiness. Filaments of galaxies stretch across the universe, their tendrils converging at dense nodes. Between them lie vast voids, gargantuan, almost empty bubbles, where very few galaxies reside. This is the architecture of the universe, its cosmic scaffolding revealed: walls, strands, and voids, the cosmic web.
These filaments and walls are not random. They follow the contours of dark matter, the mysterious invisible substance that outweighs normal matter by 5 to 1. Though we cannot see dark matter, its gravitational pull sculpts the universe. It gathers galaxies into clusters, clusters into superclusters, and aligns them into this grand lattice. One of the most profound discoveries of modern cosmology is that this web-like structure exists at all, that the universe has texture, rhythm, and form. It is not smooth, it is not simple, it is elegant.
Laniakea is one node in this cosmic web, a vast intersection connected to neighboring superclusters like Shapley and Hercules, each with their own swarm of galaxies. These connections are not coincidental. They are fossilized relics of density ripples that emerged shortly after the Big Bang. Quantum fluctuations were stretched to cosmic scales by inflation, and over billions of years, gravity turned these ripples into rivers of matter. Filaments formed, galaxies lit up at intersections, and the universe unfolded like a living organism with bones and arteries.
And yet, superclusters are not eternal. The expansion of the universe is accelerating. Over time, unbound galaxies and clusters will be carried away faster than light by the stretching of space itself. In the distant future, only those galaxies still gravitationally tethered to us will remain visible. The rest will vanish from view. This means superclusters are not just structures of space, they are windows in time. We live in a brief moment when the universe's grand design is visible, when its filaments can be mapped and studied. This visibility will not last forever.
Among the most magnificent examples of this design is the Sloan Great Wall, stretching 1.38 billion light-years, discovered into. Even larger is the Hercules Corona Borealis Great Wall, possibly the largest known structure in the cosmos, spanning up to 10 billion light-years. These immense constructs challenge the cosmological principle, the assumption that the universe is the same in all directions at large scales. If these walls exist, what else might lie beyond our current reach?
As we ascend in scale, drifting farther from our galactic neighborhood, we come to realize that the universe is not merely vast, it is organized. Each supercluster is a continent of galaxies, some densely packed, others sprawling. All are evolving, moving, colliding. Within them, stars are born, live and die. Planets orbit in quiet darkness, and perhaps, somewhere, a creature looks up and wonders how far the universe truly goes.
At this scale, we are no longer talking about places, but about relationships. How matter connects across tens of millions of parsecs. How gravity binds the cosmos into a single tapestry. Beyond even the superclusters lies the observable universe, a sphere around us roughly 93 billion light-years in diameter. This is not the whole universe, just the part whose light has reached us since the dawn of time. The expansion of space allows us to see farther than the universe's age would suggest. Light from galaxies that emitted their glow 13 billion years ago now comes from places more than 30 billion light years away thanks to the stretching fabric of space. And beyond the observable, mystery, silence, a darkness not of absence but of distance, a region where light has not yet arrived. Perhaps other superclusters live there, stranger structures shaped by unfamiliar physics. We do not know, but the mere possibility is staggering.
In the end, superclusters are more than cosmic geography. They are symbols of our expanding understanding. Once, we thought Earth was the center of it all, then the Sun, then the Milky Way. Now we see that our galaxy is a speck in a local group, itself a speck in a cluster, itself a speck in a supercluster, a ripple in the cosmic ocean. The universe speaks to us in the language of light and gravity, in filaments and voids, and we are finally beginning to listen. We linger now among the superclusters, these grand cities of galaxies, humbled by their scale, inspired by their elegance, and somewhere in the faint glow of a quiet galaxy on the edge of Laniakea, a species dares to wonder, how big is the universe really?
Every telescope, every satellite, every radio dish we've ever built, all of them peer into this same sphere. Everything we know, everything we've discovered, lies within this boundary. It is, in a way, our cosmic prison. We cannot see beyond it, not because we lack the technology, but because the laws of physics forbid it.
At the very edge of the observable universe lies a faint, ancient light. This is the cosmic microwave background, the afterglow of the Big Bang. It is not the edge of space, but the edge of visibility, a kind of cosmic curtain. This faint radiation comes from a time just 380,000 years after the universe began. Before that, the cosmos was opaque, a hot, dense soup of particles and radiation that scattered light like a fog. When the universe cooled enough for atoms to form, light could finally travel freely. That light has been traveling ever since. What we detect today as the microwave background is that very light, stretched into long wavelength by billions of years of expansion. It is the oldest light we will ever see. Staring at the cosmic microwave background is like looking at a photograph of the universe as a baby, and it is this ancient image that sets the outer edge of our observable universe. Beyond it lies something we can't see, not because it's not there, but because we are looking through time as much as through space. So what lies beyond the observable universe?
This is one of the greatest unanswered questions in modern cosmology. The most widely accepted theory is that the universe continues beyond our observable limits, that it stretches on, perhaps infinitely, that there are galaxies out there, uncountable, unreachable, invisible, existing in a space we will never observe.
If that's true, then the observable universe is like a tiny island floating in a vast dark ocean, an island that just happens to be where we live. Some scientists suggest that if the universe is truly infinite, then every possible arrangement of matter must occur somewhere. That means somewhere out there, billions of light years beyond our vision, there could be another Earth, another you, a region of space where particles randomly arrange themselves into a mirror image of our world. It sounds like science fiction, but mathematically, it's a real possibility in an infinite universe. Others believe the universe might be finite, but unbounded, curved back on itself like the surface of a sphere. In that case, traveling far enough in one direction would eventually bring you back to your starting point. Although you'd never realize it, due to the expansion of space, the light from your starting point would never catch up to you. But there's another idea, perhaps even more intriguing, that what lies beyond the observable universe is not more of the same, but something fundamentally different. That the space beyond may contain different laws of physics, different constants, even different dimensions. This leads us into the domain of the multiverse. According to some models of inflation, the rapid expansion that occurred in the first moments after the Big Bang, our universe is just one bubble in a vast cosmic foam. Each bubble represents a different universe, a separate reality. In some of these bubbles, gravity might be stronger or weaker, atoms might not form, stars might never ignite. Life, as we know it, might be impossible, and yet these other universes may be just as real as ours, even if we can never see them.
In this view, the observable universe is just one page in a vast cosmic book. We're reading our page, studying every detail, but the other pages are closed to us forever, sealed by the speed of light and the structure of space-time. What lies beyond the observable universe could redefine everything we think we know. But even within our visible sphere, the limits of understanding are profound. For instance, we know that the universe is expanding, but not only that, it's expanding faster over time. Galaxies farther away are not just receding from us, they are accelerating. This discovery led to the concept of dark energy, a mysterious force driving the universe's accelerated expansion.
Dark energy makes up about 68% of the universe. Dark matter, which holds galaxies together, makes up another 27%. The rest, the stars, planets, gas, dust, and all of us, accounts for just 5%.
That means most of the universe is composed of things we cannot see, cannot touch, and cannot fully explain. The observable universe is filled with mysteries, even within its visible edge. And the edge itself, what does it really mean? It's not a physical wall. If you travel toward it, you wouldn't crash into anything. In fact, from any other point in the universe, the observable sphere would look different. Every observer has their own bubble, centered around them.
The universe has no center, and it has no edge in space, only in time and visibility. That means the observable universe is a personal horizon. It moves with you. It changes over time. As the universe ages, light from more distant regions reaches us, slowly expanding the sphere.
But because of the accelerated expansion, some parts of the universe are receding so quickly that their light will never reach us. Not now, not ever. Eventually, more and more galaxies will drift beyond our view. In the far future, our night sky will grow empty. The stars will fade. The galaxies will vanish, and the observable universe will shrink, not in size, but in content.
What was once a sky filled with 1 trillion galaxies will become a lonely, dark expanse, a cosmic island with no neighbors. We are fortunate to live in an era when the universe is still visible, when light from the farthest reaches is still arriving, when we can still map the structure of the cosmos and ask questions about its origin. Future generations, billions of years from now, may not have that luxury. They may live in a universe that feels empty, a universe whose true vastness has slipped forever beyond their reach. So we stand now at the edge of knowledge, the edge of light, the edge of time. What lies beyond the observable universe may forever remain unknown, but perhaps that is part of the wonder. The mystery invites us to keep asking, keep searching, keep imagining. It reminds us that no matter how much we learn, there is always more to discover. As we zoom out to this ultimate scale, we see not just space, but possibility. We see a universe that defies comprehension, one that may be infinite, or may loop back on itself, or may be one of countless others. And in the face of this overwhelming immensity, we are not diminished, we are elevated, because we are here, We are looking. We are listening. The observable universe is a window. Through it we see not only what is, but hints of what might. And though we cannot yet step beyond that window, we can imagine, we can dream. And sometimes that is enough to keep the journey going. So as we end this cosmic zoom, starting from Earth and traveling across solar systems, galaxies, clusters, superclusters, and now to the very edge of what is visible, remember this: we are part of something far greater than we can ever measure. A universe whose vastness inspires awe. A universe whose secrets call to us across the stars. A universe whose edge is not the end, but the beginning of our greatest questions. And somewhere floating in the quiet stillness of space, you are here, watching, wondering, and reaching for what lies beyond.
We began this journey on Earth, our tiny blue home spinning in the vastness of space. From here we zoomed out, farther than the eye can see, past the moon, past the planets, out into the stars, across the Milky Way, through galaxies and superclusters, into the edge of the observable universe. We saw it all: the beauty, the structure, the scale.
And now we return, not because the journey is over, but because sometimes, to truly understand the universe, we have to come back to ourselves. The more we zoomed out, the more we realized something profound, that while the universe is vast, its story is also deeply personal.
You are part of this. You are made of stardust, formed in ancient stars, sculpted by cosmic forces. The iron in your blood, the water in your cells, the light in your eyes, all of it came from out there.
You are not separate from the universe. You are a moment of it, a spark of awareness in a sea of galaxies. And that changes everything.
In a cosmos so large it defies comprehension. Your existence may seem small, but it is not meaningless. It is rare, it is powerful, it is conscious, and that makes it extraordinary.
Because while galaxies spin, stars burn, and light travels billions of years through space, it is here, on this small planet, that something truly miraculous has happened. The universe has become aware of itself through you. When we ask, how big is the universe, we're really asking, where do we fit into it? And maybe, just maybe, the answer isn't about size. It's about connection. Every star, every galaxy, every life, all of it is connected across time, across space, across generation. So, what do we do with this understanding? We take a breath, we look up, we remember that we are not lost in the universe. We are part of it. And when life feels overwhelming, when the noise of the world grows too loud, remember this: there is beauty in silence. There is peace in perspective. There is calm in knowing that you are a part of something timeless. Tonight, when the sky darkens, go outside. Find a star. Let its light reach you, a traveler from the past, touching your present, and know that you are not alone. The universe is not just out there. It is in here, in your thoughts, your dreams, your questions, and it is still unfolding, still growing, still waiting to be discovered. So, keep wondering, keep reaching, keep looking up. Because in this vast, mysterious, breathtaking universe, one of the intriguing aspects of the bulk is its potential to solve certain cosmological puzzles. For instance, it might explain the weakness of gravity compared to other fundamental forces, as gravity could be leaking into the bulk. Additionally, the existence of the bulk could account for dark matter and dark energy, as these mysterious components might be manifestations of how our brain interacts with the higher dimensional space. While the concept of the bulk remains largely theoretical, It has sparked numerous research avenues in theoretical physics and cosmology. Scientists continue to explore ways to test these ideas and search for observable consequences of living in a universe that might be just one part of a much larger multi-dimensional reality.
Brain collisions represent a fascinating concept in theoretical physics, offering a potential explanation for the creation of new universes. In this model, our universe exists as a three-dimensional membrane or brain floating in a higher dimensional space. Other brains may exist in this same space, and occasionally these brains might collide with one another. When two brains collide, the enormous energy released could spark the formation of a new universe. This process is somewhat analogous to the Big Bang theory, but instead of emerging from a singularity, the new universe would be born from the interaction between two existing cosmic structures. The collision would release an immense amount of energy, potentially creating matter, space, and time as we know them. This idea stems from string theory and M theory, which propose the existence of extra dimensions beyond the four we can observe. These theories suggest that gravity, unlike other fundamental forces, can leak between brains, explaining why gravity appears weaker than the other forces in our universe. While brain collisions remain a highly speculative concept, they offer an intriguing alternative to traditional cosmological models. If true, this would imply that our universe might be just one of many in a vast multiverse, each created by cosmic collisions on an unimaginable scale. However, detecting evidence of other brains or collisions remains a significant challenge for modern physics.
The episodic universe model offers an alternative explanation for the origin and evolution of our cosmos. This theory proposes that our universe began not with a sudden expansion or Big Bang, but through the collision of two vast, flat membranes or brains in a higher dimensional space. In this scenario, these brains exist in a realm with more dimensions than the three spatial dimensions we observe. They move through this higher dimensional space, occasionally colliding with each other. The energy released during one of these collisions is believed to have sparked the creation of our universe.
Brain cosmology, which forms the foundation for the episodic model, suggests that our entire universe exists on a three-dimensional membrane within a higher dimensional bulk space. This concept stems from string theory, which posits that the fundamental constituents of the universe are tiny vibrating strings of energy. The episodic model attempts to address some of the challenges faced by the traditional Big Bang theory. It offers explanations for the uniformity of the cosmic microwave background radiation and the flatness of space, without requiring a period of rapid inflation. Instead, it proposes that these features arose from the nature of the brain collision and the subsequent evolution of the universe.
Brain cosmology offers an intriguing approach to addressing the hierarchy problem in physics, which puzzles scientists due to the vast difference between the strength of gravity and the other fundamental forces. This theory proposes that our universe exists on a three-dimensional membrane or brain floating within a higher dimensional space called the bulk. In this model, gravity is not confined to our brain but can spread out into the extra dimensions of the bulk. This spreading out or dilution of gravity could explain why it appears so weak in our three-dimensional world compared to the other forces. The other fundamental forces, in contrast, are thought to be confined to our brain, maintaining their full strength. The existence of extra dimensions in brain cosmology also suggests that the true scale of gravity might be much closer to that of the other forces than we observe. The apparent weakness of gravity in our world could be an illusion caused by its dispersion across these hidden dimensions. This concept provides a potential solution to the hierarchy problem without requiring the introduction of new particles or forces in our observable universe.
Brain cosmology not only addresses the hierarchy problem, but also opens up new avenues for understanding other cosmological mysteries, such as the nature of dark matter and dark energy. While this theory remains speculative and requires further evidence, it represents an innovative attempt to unify our understanding of the fundamental forces that shape our universe. Brain cosmology theories propose that our universe exists on a multidimensional membrane or brain within a higher dimensional space. While these theories remain speculative, scientists have considered several potential observational signatures that could provide evidence for their validity. One intriguing possibility is the detection of gravitational waves with unexpected frequencies or amplitudes. According to brain theories, gravity might be able to propagate through extra dimensions, potentially leading to gravitational wave signals that deviate from the predictions of standard general relativity. Advanced gravitational wave detectors could potentially pick up these anomalous signals, offering a window into higher dimensions.
Another avenue of investigation involves searching for slight variations in the strength of gravity over very large distances. Some brain models predict that the force of gravity might behave differently on cosmic scales compared to what we observe in our local environment. Precise measurements of galactic motions and the expansion of the universe could reveal these subtle deviations, providing support for brain cosmology. Cosmic microwave background radiation, the afterglow of the Big Bang, might also hold clues. Brain theories suggest that our universe could have collided with other brains in the past, potentially leaving observable imprints on this primordial radiation. Detailed analysis of the cosmic microwave background could uncover patterns or anomalies that align with predictions from brain cosmology, offering tantalizing evidence for these multidimensional models. Brain cosmology presents a radical departure from traditional Big Bang theory, offering a new perspective on the origin and structure of our universe. In this model, our universe exists as a three-dimensional membrane or brain floating within a higher dimensional space called the bulk. This contrasts sharply with the standard Big Bang model, which describes our universe as a singular four-dimensional space-time continuum. The key difference lies in how these models explain the beginning of the universe.